Welcome to our lecture online. Our next example is a very interesting example. It's an exponential function. And when you look at it, you say f of x equals 2 times e to the x plus 1/8 e to the minus x. And we're supposed to find the arc length from x equals 0 to x equals the natural log of 2. Again, it's not explicitly stated, but those are x limits. And here, of course, is our general format of the integral that we're supposed to solve. Now, you may think that, oh, if you can solve this one, you can solve almost anything like that, but that's not at all the case because that function was very specifically chosen to make it relatively easy to do the integration. Many exponential functions will not be that easy, just be forewarned. But at least it's a simple example again, so we can learn the technique for various types of functions, in this case an exponential function. So let's go ahead and see how that's done. Our function here, 2e to the x plus 1/8 e to the minus x. We take the derivative, we get 2e to the x minus 1/8 e to the minus x. Then when we square it, we simply take that and square it. When it's multiplied out, we get that. So now we plug that into our general format. So we know that the arc length L is equal to the integral from 0 to the natural log of 2 of the square root of 1 plus that function squared, which is 4e to the 2x minus 1/2 plus 1/64 e to the minus 2x, not the terrible looking e, let's try that again, like that, okay? Extend that out, times dx. Now notice what happens here. We have a plus 1 here and a minus 1/2. When I combine the two, this turns into the following. L is equal to the integral from 0 to the natural log of 2 of the square root of 4e to the 2x plus 1/2 plus 1/64 e to the minus 2x times dx. Now normally you would look at this and say, how can I possibly integrate that? But it turns out that this is a perfect square. This cannot be reduced to the following. L is equal to the integral from 0 to the natural log of 2 of the square root of the quantity 2e to the x plus 1/8 e to the minus x quantity squared. Because remember, when we had this with a minus sign, we end up with that. But now it turns out that you get the same result, but with a plus sign, because this is plus 1/2 instead of minus 1/2. So we end up with the same thing here, but with a plus. So that's why the numbers, the equation was carefully chosen so that you'd be able to do that. Because now you can say, all right, that means that L is equal to the integral from 0 to the natural log of 2. And the square, of course, negates the square root. So we end up with, don't forget my dx there. We end up with 2e to the x plus 1/8 e to the minus x quantity dx. And of course, this is easy to integrate. So this becomes equal to, when we integrate 2e to the x, that becomes 2e to the x. When we integrate this, we get the same, but this becomes now minus 1/8 e to the minus x, evaluated from 0 to the natural log of 2. All right, now we evaluate that, so we get L is equal to, when we plug in the upper limit, we get e to the natural log of 2, that negates each other, so we have, that's 2 times 2 is 4, minus 1/8 times e to the minus natural log of 2, that's the same as 1/e to the x, evaluate the natural log of 2, that gives us 1/2, so times 1/2, minus, when I plug in the lower limit, e to the 0, that's 1, so I get 2, and minus, this becomes 0 again, 1/8. All right, now we have to be very careful about the numbers and the signs. So we end up with, this is equal to 4 minus 1/16 minus 2, minus times the minus, it would be plus 1/8. All right, so that gives us 4 minus 2, which is 2, and 1/8 minus 1/16, that would be plus 1/16. So that would be 32 plus 1, or 33/16. And that would be the arc length from x equals 0 to the x equals natural log of 2. Notice it's slightly over 2, which makes sense because the natural log of 2 is a little less than 1. And so have that curve there, probably a little bit steeper curve, so it seems reasonable for that answer that it would be about 33 over 16. And that is how it's done. Now remember, again, it was easy, relatively easy, because the function was chosen just perfectly so. And that is why it looks relatively easy.